Last week, we have talked about Pascal triangle, that is a number in a triangular shape.
1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 1, and so on and so forth.
Each of these numbers is called a binomial coefficient and can be represented by this symbol and choose k. So last week, we defined Pn to be the product of n choose k from k equals to 0 to n. We have proved that Pn minus 1 over Pn equals to n factorial over n to the power of n. This is 1, 2, 3, up to n, and each of these is over n. It can be understood by taking the number in n rows divided by the number at the bottom left hand side. Example, 1 over 1, that is 1.
1 over 1, that is 1. 1 over 2, that is a half. 1 over 1 is 1. 2 over 3, 2 over 3, 1 over 3. Then 1 over 1, 3 over 4, 3 over 6. 3 over 6 is actually 2 over 4 and 1 over 4. Then 1 over 1, 4 over 5, 6 over 10, that is 3 over 5, 4 over 10, that is 2 over 5, and this is 1 over 5.
And this can continue, and in general, Pn minus 1 over Pn will be equal to this one. Now for this week, we are going to prove that the limit of this term will be equal to 1 over e. In other words, we are going to show that the limit of n factorial over n to the power of 1 over n and go to infinity equals to 1 over e. First, we consider the log of this term. Since this is a log, it can be written as the limit of 1 over n log of n factorial over n. That is 1, 2, 3, all the way to n over n. We know that log of AB can be written as log A plus log B. Since we have this, then this can be written as 1 over n log of 1 over n plus log of 2 over n plus log of 3 over n all the way to log of n over n, where n go to infinity. Initially, the product of the terms become the sum of the log, and this can be written as the limit n go to infinity 1 over n summation log k over n, where k equals 1 to n. For those who have learned some calculus, then you can recognize that this is in fact equal to integration from 0 to 1 log of x dx. It is so because the Riemann sum say that limit of 1 over n summation f of k over n, where k equals 1 to n, where n go to infinity, this will equal to integrate 0 to 1 fx dx. Then we have to do the calculation here. Now, for this calculation, it will be easier if we do a little bit of a change. The graph of y equals to log x is as shown. So we are going to get the area under the curve from 0 to 1. If we reflect about the straight line y equals to x, then we will have this curve. And this curve is y equals to ex, where this is 1. The area here is actually equal to the area here. But note that this area is of a negative value. So this is exactly equal to negative infinity to 0 ex dx. But bear in mind that this is a negative value. This is so-called an improper integral. Then we should write it as negative limit a go to negative infinity from a to 0 ex dx. And when we do this, this will be negative limit a go to negative infinity, and this is ex from a to 0. Okay, let me continue here. So this is equal to a negative limit a go to negative infinity, sub in x equals to 0, sub in x equals to a. When a is going to negative infinity, e to the power of a is equal to 0. So this is gone. And e to the power of 0 is equal to 1. So the answer is negative 1. So what we have here is the limit of log of this term is equal to a negative 1. Let me write down the result here. So what we have just now, this is equal to negative 1. And how we relate this back to the original limit? Why this is equal to 1 over e? For any number a, you can write as e to the power of log a. And because of this, the original limit
n go to infinity, n factorial n to the power of 1 over n.
It can be written as the limit of n go to infinity, e to the power of log of n factorial n to the power of 1 over n. And because ex itself is a continuous function, then we know that the limit of f hx, where x go to a, can be written as f of limit hx, where x go to a, if f is continuous. So in this case, it can be written as e to the power of limit n go to infinity, log of n factorial over n to the power of 1 over n. And since we know that this limit is equal to negative 1, and we prove that this is true. So from last week and this week, we proved something from the Pascal triangle. And next week, we'll continue with some other interesting proof from the Pascal triangle itself. See you again. Bye-bye.